Yes.
So, good morning. It's my great pleasure to introduce to you Professor Magdalena Stobinska. She's a professor at the Faculty of Mathematics, Informatics, and Mechanics of University of Warsaw. She holds both a master and a PhD degree from the Faculty of Physics of the University of Warsaw. And then she moved to Germany, first as a Humboldt scholar in Max Planck Institute in Erlangen, and then she worked in the university in Erlangen, and then at the Institute of Theoretical Physics, University of Gdańsk, and then came back to her alma mater, the Faculty of Physics of the University of Warsaw, and now, so to speak, she moved like 100 meters to the other side of the street to the math department. She's a leader of the group Quantum Technology. So her specialty is the quantum information, quantum processing, and quantum optics. So as you can see from many photos, she's in the laboratory as well. So not only theoretician, but practitioner, I think, experimentalist, I must say. She's an author of new steering method of photons, and this method does not rely on Bell inequalities, the inequalities you have heard about yesterday, but on the steering methods. And it's supposed to provide easier implementation and security in quantum technologies as such. So I'm going to make the Zoom is yours.
Hi, good morning. Thank you so much for your kind introduction. Indeed, I am a quantum physicist. I am a theoretician, but I closely work with experimentalists. Nevertheless, I try to make my best to prepare the presentation so that it's comprehensible for non-physicists, but for a mathematician, for example. Okay, so today I would like to tell you about hybrid quantum key distribution, because this is one of the latest and most intriguing trends in quantum cryptography, and in particular in key distribution problem. And one of the leaders, Europe is one of the leaders in developing this technology. And our direct competitor is China, that has recently presented an outstanding experiment demonstrating one such example of this technology. Okay, so in order to explain what's hybrid quantum cryptography, let's do a little bit of recap. Let us remind ourselves why at all we need any new classical approaches. So that would be the introduction. And later, we will quickly refresh our memory. What was it about in quantum cryptography? What is the post-quantum cryptography? And does this have anything to do with quantum at all? Now I can already tell you that not, but it makes it even more interesting. And then we will head towards the hybrid solutions. Okay, so classical cryptography. In conventional cryptography, two parties, Alice and Bob, share a communications channel, and they would like to communicate privately in the presence of an eavesdropper, Eve. The holy grail of secure communication is information theoretical security. That is an unconditional security that is independent of all computational powers of Eve that Eve may have. As Shannon has shown, this unconditional security can be achieved via one-time pad OTP method, if the two users share a long random string that is kept secret from Eve. How to distribute a long key in the presence of Eve is called the distribution problem that is central challenge in all kinds of encryption methods. All conventional key distribution schemes that rely on classical physics and mathematics provide only so-called computational security, because in classical physics, nothing prevents an eavesdropper from copying the key during the key distribution. Currently, the key distribution problem is often solved by public key infrastructure, PKI. A receiver, Bob, publishes the public key so that a sender, Alice, can encrypt a message and send the ciphertext to Bob. Bob has the private key and can decrypt the ciphertext efficiently. Given the public key, there is no efficient known algorithm for Eve to work out the private key or the plain text. For instance, the security of the best known public key crypto system, RSA, is based on presumed hardness of prime factorization. However, the Shor's algorithm enables us prime factorization on a quantum computer in a polynomial time. Therefore, since the hardness of most public key infrastructure is based on integer factorization and discrete logarithm problems, it is paramount to follow the progress in the implementation of the Shor's algorithm on quantum computers, as well as to work out quantum proof encryption alternatives. Recently, in 2020, the factoring of RSA 250 was announced. An RSA number of 250 decimal digits or 829 bits, as well as was solved, as well as a discrete logarithm problem of the same size. New records of this type are constantly being refreshed as performance of computer hardware increases over time. Two quantum-safe approaches in cryptography have been identified. One, quantum cryptography, that is based on the laws of physics, which offer a genuine information theoretical security, but it does not replicate all the functionalities of PKI and requires building a new quantum infrastructure. The second approach, the post-quantum cryptography, based on new algorithms, is compatible with the existing PKI schemes. However, it offers only computational security against currently known attacks. It has been spotted that both approaches are complementary and could be combined for achieving higher security levels. In the case of quantum cryptography, Alice and Bob employ quantum information, and in particular, quantum entanglement, though not necessarily, to solve secure key distribution problem. I would like to stress the fact that quantum key distribution protocols, QKD.
Excuse me,
yes.
I have a question about this result from 2020 about factorization of this large number. This was
Yes.
on classical computers? This was done on classical computers? This, RSA 250?
No, I think it was on the quantum platform.
On the quantum, okay.
Yes.
Okay,
yes,
I was just
yes.
confused. Okay, okay. Thank you very much.
Thank you. I'll go back to where I was. Yes, so let me stress the fact that quantum key distribution protocols can be devised that are invulnerable to any attack allowed by the laws of physics, either now or in the future. This is the key difference to the classical cryptography, where the security is based solely on the limited computational powers of an eavesdropper, and it exists only within certain time interval. So for example, these days, computational power of our eavesdropper is limited, but it can download the data and wait until another revolution in classical computer comes, the computational power increases, and then she deciphers retrospectively. Can I move my slide? Okay. All right. In order to understand where the information theoretic security of quantum cryptography stems from, let us recall, what is quantum information? Well, this is a profound question. And here we talk about its applications, and I would like to take a pragmatic standpoint. Quantum information is represented by a physical state of a quantum system, and it is governed by the laws of quantum world. Its basic unit is a quantum bit called qubit, which is encoded in a two-level quantum system. Formally, a qubit is a normalized vector in a two-dimensional Hilbert space C squared, spanned by two orthonormal basis vectors 1, 0 and 0, 1. These vectors correspond to the qubit states and are denoted in literature as ket0 and ket1. The qubit can be any linear combination of ket0 and 1 with complex coefficients alpha and beta, which is called a quantum superposition. And qubit states can form tensor product basis states in 2 to n dimensional Hilbert space. For example, two qubits can span a 4-dimensional space as shown below. So 0 times 0, it's 0, 0 ket, 0 times 1, 1, 0, 1, 0, 1 times 0, 1, 0, 1 times 1, 1, 1. Normalization of the qubit vector psi requires the following condition to be fulfilled. Modulus alpha squared plus modulus beta squared equals 1. This provides us with a statistical interpretation of its measurement outcomes. The qubit has a probability modulus alpha squared to be found in the state 0, and the probability modulus beta squared in the state 1. I don't know if you're familiar with the ket and bra notation. This is called the Dirac notation, and it's just used for convenience in quantum mechanics. But as I mentioned, you can think about it as vectors, Let us consider a simple example, a horizontally polarized photon that is measured in the circular polarization basis, RL. And let us identify the linear polarization states, H and V, with vectors the ket 0 and 1. Then we will find the qubit to be left circularly polarized and right circularly polarized with equal probability 1/2. All right. Okay, so our next step towards quantum cryptography and the hybrid cryptography is the no-cloning theorem. The no-cloning theorem is the basis for all quantum cryptographic solutions. This is a theorem. The no-cloning theorem tells us that it's impossible to perfectly clone an unknown quantum state using a unitary operator. Let's have a closer look how it actually works. We have a proof here. So let us consider a state psi in register A that we want to copy to a register B. They don't have to be any qubits. It can be just any arbitrary quantum states. And the register is initially prepared in a state S, the register B. These states may live in an arbitrary Hilbert space, And let us assume that U is a unitary operator that allows us copying from A to B. Then we produce two copies of psi. And next, let us repeat the same procedure for some other state phi. And we achieve two copies phi. Hilbert space is equipped with the inner product that is denoted like this. It's a bra psi acting on ket phi. Let us now take the inner product between the left and right sides of these two equations. Please recall that U is a unitary, and therefore U dagger times U amounts to a unit operator, and S is normalized. This leads us to an equation of the following type: x equals x squared with solutions x equals 0 or x equals 1. Therefore, either state psi and phi are orthogonal or identical. Therefore, we see that it is impossible to copy non-orthogonal states using a unitary operator. However, it is perfectly possible to copy orthogonal states. This nicely corresponds with the fact that in the end, we can copy classical messages. The no-cloning theorem, as I have mentioned, is the very basis for quantum cryptography because it does not allow us to copy quantum information without disturbance to the original system. If we try to copy, we immediately disturb the original state. But we will see how it actually works in practice in the following slides. Okay, one of the first and most
Sorry, may I have a question?
Sure, yeah.
So mathematically, it is impossible to find a unitary transformation which acts like. So could we go to the previous slide? So S is fixed here, yes?
Yes, do you see the no cloning theorem slide?
Yes.
Okay. So yes, S is, so it is, the theorem says that it is impossible to copy non-orthogonal quantum states. However, it is perfectly possible to copy orthogonal states. Yes, S is a fixed some state of a register of a target B.
So stating it mathematically, it means that there is no unitary maps which is mapping a given psi tensor S, where S is fixed, to psi tensor psi. Yes.
Yes.
Okay. Thank you.
And S is arbitrary. Yes.
Okay. Thank you.
This is a very, very simple proof, as you can see, but it's the message that this theorem carries is of extreme importance to the quantum information. Okay, so now we are ready to have a look at one of the first and seminal protocols of quantum key distribution, known as the Bb84 Protocol, where B and B stands for the surnames of Bennett and Warsaw, and 84 for the year when it was invented. Just as a fun fact, I would like to tell you that although this is one of the biggest achievements in quantum information theory and quantum information processing, I spoke in person with Mr. Bennett, who told us during the conference dinner the whole story, how difficult and impossible almost it was to publish the paper. Okay, this result was so revolutionary that was just not accepted by the scientific community for a long time. Okay, now we know that quantum distribution is a very valid research field, and the door are open for further explorations. Okay, so let us see how it works. We have, as before, a sender, Alice, and a receiver, Bob, and they want to communicate over an optical channel. Alice randomly encodes her qubits in one of the 4 polarization states of a single photon, 2 linear and 2 circular. They are denoted as horizontal and vertical and skewed arrows, respectively. Bob randomly chooses one of the 2 bases, again linear or circular, and marked as plus and x, respectively. Its measurements provide him with a collection of results. Next, Alice and Bob publicly announce their basis choices. They discard the polarization data encoded in different bases. In this way, Bob obtains a string of bits that is called a sifted key. Eventually, Alice and Bob compare random samples of their sifted key bits to compute the so-called quantum bit error rate. If this Q-bar is too high, they infer that actually Eve may have interfered and they should abort the protocol and start again. If the Q-bar is low enough to complete the procedure of the secret key generation, Alice and Bob perform classical post-processing with 2 more steps known very well from classical cryptography: error correction and privacy amplification. Please note that Bb84 protocol does not use any entanglement. Nevertheless, it has been shown to be completely equivalent to some other seminal QKD protocol that was invented by Arthur Eckert in 1992 that is fully based on quantum entanglement. This protocol is often denoted by E91, and further it was amended to a protocol BBM92. So they are still perfectly in use. Okay. What happens if Eve attacks the quantum channel? How she is being noticed by Alice and Bob? Let us consider the simplest eavesdropping strategy here, the intercept resent attack. Eve intercepts each bit sent by Alice, measures it, and next sends it further to Bob. Perfectly reasonable strategy. Let us focus on the cases now when Alice and Bob use the same basis, since they will throw away all the rest of cases. If Eve guesses correctly the basis chosen by Alice, which is 50% of times, then both she and Bob will decode Alice's bit value correctly. No error is introduced by Eve. However, if Eve uses the wrong basis, which is also 50% of times, then both she and Bob will have random measurement results. This suggests that if Alice and Bob compare a subset of the sifted key again, they will see a significant amount of errors. Thus, Eve's attack will introduce 50% Q-bar for half of the total bits and total of 25% Q-bar. This leads us to an important conclusion that an eavesdropper information gain leads to a disturbance in the measurement statistics between the sender and receiver. And this is how they spot that someone is listening. Okay, I would like to now show you 2 almost commercial implementations of the QKD protocols. This is not something that happens just in laboratories. This is already at the stage where serious field tests are in place. So many of the protocols were invented since seminal protocols such as Bb84 and E91, and much of development took place. Many of them have awaited genuine field tests and became a true quantum technology that is on the brink of commercialization with a wider adoption. The first such example of implementation is by Toshiba. These pieces of equipment that we see, this is exactly Alice and Bob that are connected by a fiber. So this implementation is a fiber implementation because the quantum signals are sent through a fiber network. In 2018, Toshiba, that collaborates with the Cambridge University, proposed so-called twin field QKD protocol that enables efficient quantum communications over hundreds of kilometers. And demonstration was done for fiber link of the length of 240 kilometers. And in 2021 for 555 and later for 600 kilometers lengths. They have achieved key rates of 300 kilobits per second for 120 kilometers, 1.77 bits per second for 555 kilometers, and 0.778 bits per second for 600 kilometer link. The second implementation is satellite-based and has been done by a Chinese group led by John Wei Pan. Here, the quantum signals are sent over the free space through a satellite connection from the satellite to the Earth by downlink to the Earth. In 2016, China launched its MIMUW satellite and demonstrated the first entanglement distribution between the ground stations separated by 1,200 kilometers. Then an experiment linking China and Austria with quantum encrypted video call over 7,600 kilometers was conducted in 2018. Next, in 2020, this satellite was used for the first QKD protocol over 1,100 kilometers with the bit rate of 0.21 bits per second. Finally, in 2021, it became a part of 4,600 kilometer long quantum Chinese network involving free space and fiber networks. Okay, QKD is a disruptive technology. However, it requires a lot of investment. Just like cell phones, it requires building a whole new infrastructure to be implemented. In addition, currently achieved key rates are rather low, much lower than the demand, especially for the long-distance communications. Therefore, in 2016, NIST, National Institute for Standards and Technology in the US, published a report on PQC 20, anticipating that a quantum computer is likely to be built by 2030 that breaks 2000-bit RSA in few hours and therefore renders the current public infrastructure insecure. Alternatives that are quantum safe and compatible with existing telecom infrastructures have been identified as of high demand. In the same year, NIST initiated the post-quantum cryptography standardization process by announcing a call for proposals of quantum-resistant cryptographic primitives, including public key encryption, digital signature, and quantum exchange algorithms. This process is expected to release the standardization documents by 2024. The post-quantum cryptography, despite its name, has nothing in common with quantum mechanics and quantum solutions. It is solely based on problems that are believed to be computationally hard for conventional computers and that are not threatened by the Shor's algorithm. That means these are problems beyond the integer factorization and beyond the discrete logarithm problem or the elliptic curve discrete logarithm problem. Therefore, PQC can offer only the computational security. There are several different types of PQC, out of which the following two are the most popular. Most often discussed these days. The lattice-based PQC, and that relies on lattices over vector space or free modulus, and code-based PQC that rely on error-correcting codes. Today, I would like to focus solely on the lattice-based PQC for the reason of this demonstration that I will discuss in the following slides. And therefore, I would like to just give you a taste to highlight the two types of hard problems on which lattice-based PQC is often based. The first is the learning with errors problem, LWE. This is a computational problem of inferring a linear function over a finite ring from given samples, and some of these samples may be erroneous. This problem is conjectured to be hard to solve, and the best known algorithms require O of 2 to n operations, exponential time and computer memory, to tackle it. It gives rise to, for example, public key encryption and identity-based encryption. The other problem is the shortest vector problem, SVP, for a given lattice L, a basis of a vector space V and a norm N. One must find the shortest non-zero vector in this vector space as measured by the norm. Solving this problem also consumes time exponentially, and it finds applications in public key crypto systems. Okay, so now we are ready to head towards the hybrid quantum classical cryptography. And here I would like to show you the idea of the hybrid cryptographic approach, that the problem that it stems from. Because we have already quantum cryptography, we have already post-quantum cryptography, why at all we are looking at some other options? We're searching for hybrid solutions because although QKD can provide information theoretically secure key exchange even in the era of quantum computers, it requires authentication of its classical channel. You remember, Alice and Bob talk to each other, they have to compare the basis they have chosen, and this is this classical channel that needs to be authenticated. The authentication is executed by exchanging the seed keys, which distribution is still an open problem. It can be solved by using, for example, the one-time path method, which will be information theoretically secure. However, it suffers from the distribution problem. So Alice and Bob would have to meet in person to exchange these seed keys, which is inconvenient. Therefore, public key infrastructure is used instead, so they don't have to meet. But PKI compromises the security level and opens the security gap. On the other hand, we know there already exists a mature PKI that, if combined with a PQC algorithm, may elevate its security level and offer a Shor-resistant computational security solution. By combining a short-term security of a post-quantum cryptography algorithm, we may achieve long-term security of the keys distributed by quantum key distribution, that is Shor's algorithm proof. Okay, The group of, again, Zhang Weipan in China has recently experimentally demonstrated one such example of hybrid approach. Interestingly, in this demonstration, the QKD part was based on a Bb84 type of a protocol with polarization encoding. So photons were, the information was encoded in photons polarization, as we discussed. It was amended by a PQC authentication. This result has demonstrated an additional benefit, not only elevated security, but also another benefit. Usually, for a QKD network of n users, it is required to exchange n times n-1/2 pairs of symmetric keys to realize a pairwise interconnection. In contrast, in this new approach, with the help of a PKI and PQC, each user only needs to apply for one digital certificate from the certificate authority to achieve an efficient and secure authentication for QKD. This reduces the connectivity load from O of n squared to O of n. Let me once again emphasize that although PQC can be used for both encryption and authentication, it is believed to be secure against Shor's algorithm. PQC is still not an information theoretically secure method, and it is still an open question whether PQC is secure against other classical or quantum algorithms beyond Shor's algorithm. Therefore, it seems reasonable to assume that PQC is good for a short-term security, like authentication, but not for long-term security, such as key for coding information. Okay, so let's have a look at the details of this demonstration and more profoundly into the motivation. Where is the problem that we are solving? While QKD solves the secure key distribution problem, it needs a patch for its classical channel authentication problem. QKD includes the quantum channel that transmits the photons between Alice and Bob, and the classical channel that is used by them in post-data processing. The unconditional security of QKD does not require the classical channel to be confidential, but it requires it to be authenticated. Otherwise, a man-in-the-middle attack can occur. As the middleman, Eve pretends to be a legitimate party. She cuts off the quantum channel, reconnects the legitimate parties, and carries out the man-in-the-middle attack. This is exactly the intercept resend strategy that we just discussed in case of the Bb84 protocol. The current secure authentication method is to pre-share a small amount of symmetric seed keys and encrypt and decrypt the hash value of classical messages, just as shown in this graph. The QKD transmitter, green, sends quantum signals, psi, through a quantum channel to the QKD receiver, and the receiver carries out data processing via a classical channel and by exchanging classical messages. To authenticate the classical messages, Alice and Bob each generate a digest using a hash function H. And in this case, in this experiment, the SM3 hash algorithm was used. Next, Bob encrypts his digest with a pre-shared key, K, or Bob's private key, SB, and subsequently sends the tag to Alice. After receiving the tag, Alice decrypts it with the same pre-shared key or Bob's public key and compares the results with her own digest. If the two are the same, the authentication is successful. Otherwise, the authentication fails. And in this figure, it's just shown that Alice authenticates Bob's identity, but in the experiment carried out, two-way authentication was performed. This method can guarantee the information theoretical secure authentication, but just in principle, not in practice. It also allows us to connect with any two users in the network. However, this method is not scalable. If the number of users in the network is n, the number of the pre-shared key pairs scales quadratically with n. Symmetric keys are generally pre-shared face-to-face, and when the number of users is large, the burden is very heavy and inefficient. For example, for 100 people, we would need nearly 5,000 pre-shared key pairs and meetings. Okay. At the same time, each user needs to store the authentication key pairs with all other users. This storage, synchronization, and management of so many key pairs increases the complexity and jeopardizes the network from the security point of view. One solution is to use a trusted relay to form a star-type network. This is how it's usually done these days, for example, with mobile phones. And each user connects and pre-shares one key pair only with a trusted relay. But this reduces the interconnection between the users. We would like them to talk directly to each other. Moreover, when new users join a QKD network, they need to pre-share symmetric keys with a trusted relay and the original users on demand. If the new users QKD task is urgent, it might be too late to do all these steps. Another type of secure authentication method is to use post-quantum public key algorithm and public key infrastructure. Then each user receives a digital certificate signed by a trusted certification center, which contains his or her identity, public key, and other data required by the PKI standard. Then, for a network of n users, the number of the digital certificates drops down to n. If a new user joins the QKD network, he or she needs to obtain just one digital certificate. Therefore, the authentication based on the public key algorithm can solve the problems of the pre-sharing symmetric keys. As long as the PQC algorithm is secure during the authentication, the security of this round of authentication and the key generated by QKD is guaranteed. Even if the PQC algorithm is cracked in the future, the security of the previous authentication and keys is not affected. Therefore, we need to assume just the short-term security of PQC algorithm. This is very different from using the PQC algorithm for confidentiality or key distribution, which requires long-term security of it. The PQC algorithm that was used in this experiment is IGC, which is an efficient lattice-based digital signature scheme from variants of the learning with errors and shortest integer solutions problems. Shortest integer solution problems is very much related to the shortest vector problem. It is based on this problem. It has been shown that these two problems are at least as hard as the worst case lattice problems for certain parameter choices. And therefore, the post-quantum security of this algorithm is based on the conjectured quantum resistance of the underlying lattice problems. Importantly, it has not been found that quantum algorithms have any substantial advantages over classical ones in solving lattice problems. Let us now see how the PQC-based authentication protocol looks like. So Alice and Bob exchange their own certificates and random nodes with each other. Then they use the public key of certificate authority to verify that the other public key belongs to the identity, belongs to its identity, and use the PQC algorithm to sign the message digest and the nonce under their own private keys to generate signatures. Afterwards, they use the confirmed public key of the other to verify the correctness of the received signatures. Because only the legitimate party has the corresponding private key, it can be confirmed that the message is signed legally. In the experiment, the application of PQC in the QKD point-to-point link, so Alice to Bob speaks to each other directly, was realized with the fiber distances ranging from 10 to 100 kilometers. On the graph below, we see the key rate expressed in kilobits per second as a function of the fiber length in kilometers. The secure key rate decreases exponentially with the fiber length, which is completely consistent with the theoretical expectation for the Bb84 protocol. But I would like to stress that not all QKD protocols suffer from this unfavorable key rate distance scaling problem. This is the feature of early stage protocols like Bb84 or E91. However, there are these modern higher level protocols, for example, the twin field QKD protocol that I mentioned earlier, executed by Toshiba, that solve this problem. QKD networks can be generally divided in two types. And in order to understand how the reduce of the load from O of n squared to O of n was achieved, let us take a closer look on QKD communications network topologies. First, all-pass network, the upper graph. Here, the users are connected by optical switches, OS. To achieve an arbitrary connection between users, each user must have a QKD transmitter and receiver. Trusted relay network is another topology. It simulates the metropolitan area networks. A user must first connect to its closest trusted relay, and next the relay talks to another relay, and only then the second relay connects to the other end user. If pre-shared key authentication is used for the relay network, new users need to pre-share key with the relay and can perform QKD only with the relay, not with the other users. This reduces the interconnectivity. For the all-pass network, each new user needs to pre-share 10 pairs of symmetric keys with 10 original users and 1 pair of keys between the two new users. A total of 21 pairs of keys need to be pre-shared to achieve a connection between any two users in the network shown on the right-hand side. If PQC authentication is adopted, trusted relays can be replaced with optical switches. Each new user needs to apply for only one digital certificate, and a total of 2 digital certificates is completely sufficient to realize the connection of any two users. This greatly increases the accessibility of the network. Some results achieved in this experiment for the all-pass network that was realized in 2 different topologies, a ring connection upper and the cross connection below. In the table, we see the length of kilometers, of the total length of the fiber in kilometers, so ranging from 50 to 90, the losses encountered, and the key rates achieved, and the Q-bar in percent, the Q-bar registered. So interestingly, we see that key rates as high as 70 the range of 60, 70 kilobits per second were achieved with relatively low Q-bursts. Thank you very much for your attention. I would like to introduce my group with whom I work on all the protocols, all the problems in quantum technologies. We are very happy always to welcome new group members. So if you are interested or you have any question with regard to the lecture or quantum technologies, please drop me a line. This is my email and the address of my research group. Thank you so much.
Thank you very much. Are there any questions or comments from here or from online? Maybe I will ask a question because you announced the possibility of joining your group. How much of a quantum mechanics is needed, not only to work in your group, but just to trying to to be involved in this subject?
I have to say that if someone is interested in quantum theory at all, quantum optics or quantum information processing from the quantum photonics side is the easiest way to get involved. I will not talk about opinions. I will just give you a fact. I have a postdoc who is extremely talented. His background was classical condensed matter, so something very far from quantum theory, and he got involved into quantum communications, I think in 3-4 months. So really not a lot of quantum theory is needed to start. So don't be scared. Recently, that there is a high demand. As you know, there is a lot of development in the quantum computers, but quantum computer is not just the hardware. I'd like to say that it's mainly quantum algorithms, and there is a lot of stagnation in this field. So there is a really high demand for mathematicians and computer scientists who have some background in algorithms, who would be willing to collaborate with quantum groups. So just forget about not knowing quantum mechanics. This is something that you will learn in the flight. And there are a lot of fascinating problems on which physicists, mathematicians, and computer scientists are already working together towards developing quantum technologies. So
because you said 4 months for the physicists not knowing quantum theory, but for a mathematician probably should take a couple more months, I guess.
Mathematicians are very efficient. They already know the whole theory because quantum mechanics is basically linear algebra. So I think the biggest challenge if you are approaching quantum topics is allowing to a little bit relax so-called common sense, because as we know in quantum theory, a different philosophy obeys. The laws of quantum physics are quite contradicting our common sense, and this is something that we just have to learn to accept, and that's it.
You mentioned two rather now classic algorithm of sending encrypted messages. Do you think that there's still there was something quantum mechanics you don't know, that there will be something else, something new, spectacular, or this is just now to sort of putting us, we mathematicians say, epsilon and deltas and just refining the system, or there is a hope to some great discoveries on this on the level of quantum mechanics will foster further developments in this cryptography?
I'm sure there are always surprises in physics. There are people who work on theory that is beyond quantum mechanics. So quantum mechanics, classical physics is a part of quantum mechanics. So there was a question, what is quantum mechanics part of? So yes, I hope so. And there are a lot of fascinating open problems. There have been results showing that certain quantum mechanical systems are actually a great example of the Gödel's theorem, incompleteness theorem, that certain problems are incomplete. They are just not algorithmically definable. There are new results demonstrating the first new results demonstrating that noisy, early stage noisy quantum platforms, quantum computers, indeed do have a computational power that exceeds the computational power of classical machines. So there are always, there is always hope to find something new.
Thank you. Are there any questions or comments?
Well, I just would like to make a comment. Thank you very much. The lecture was very illuminating. It was great. I mean, very well prepared. I think great for students. Thank you very much.
Thanks. Thank you.
Maybe some questions from okay, go ahead, Frank.
Yes, so it's just a question of understanding. Could you go back, please, to the slide of the no cloning theorem?
Sure.
So it's a theoretical question.
Let me share again. Can you see my slides?
Yes, I can see them.
Okay, where is no cloning? Cloning is here. Oh, no. Okay, can you see it?
Now I can see it. Thank you.
Okay. Mm-hmm.
So the first question, maybe also in addition to the question from the colleague about the operator U, and this operator U actually is a tensor product of one tensor U. Is that correct? And this U is an operator which is defined on an C2 space and maps S into psi with respect to register B. This is my first question of understanding. Is this the action of U?
I think U is completely any arbitrary unitary operator, and that acts on registers A and B, and therefore I don't think it needs to be a tensor product of U times 1. It can be just anything that acts simultaneously.
Okay. Yeah. Okay. Yes, and then my second question is in relation to the first equality below. So taking the inner product of these two equations gives, and then you have this equality. Where does this come from?
It comes directly from the two lines above. So let me, how can I have a pointer here?
Yes, I see your pointer.
Pointer options.
We see your
you see my mouse? Okay,
your arrow,
okay.
Yes.
Yeah.
Okay. So okay, before I answer, please have a look at this object here. As you know, there is an inner product in Hilbert space. This is a scalar product of a vector and it's and a vector that is dual, and it is denoted like this in quantum mechanics. This is actually an integral of two wave functions, phi and psi complex conjugate over the entire space. We just denote it like this briefly. So if I am just computing exactly that kind of object, excuse me, below, and my right-hand side is just this line here, And my left-hand side is this, but Hermitian conjugated. So in this way, I take a Hermitian conjugation and replace cat with bra, so this object here, and I evaluate its scalar product.
I understand the technique, but let me ask it a slightly bit differently. So if you take the inner product of S, and then you have U dagger US, so but U dagger, you can put it on the left side, it gives then a cat US, so you have then the norm of US squared. But if you have the norm of US squared, if I understand this correctly, it's the norm of psi squared, psi b squared. Or am I wrong here?
I'm not sure if I follow, so I will repeat then. So yes, I'm putting US phi here and Hermitian conjugation of this object here. So I have U dagger, bra psi and bra s, and then I am computing the inner product of a register B with register B and register A with register A correspondingly, and also taking into account that U is a unitary, and therefore I don't have to first compute how it acts on S and phi. I can immediately collect U dagger and U to a unit operator.
Yes, I understand.
And then it cancels, and then I have S acting on S, which is 1 because it's normalized. State in quantum mechanics always has to be normalized, so it cancels out, and I am left with psi acting on phi here.
So the left side, that's clear to me, but not the equality to the right side. This is just a question of understanding. Perhaps I'm missing here a point. So I understand.
Is it clear now? Or?
No, not the right side. So
the right side. Okay. So the right side. Please have a look at these lines here. So U acting on psi and S, we presume that it should give us 2 copies of psi, one in A and one in register B, the other one in register B. Now, the same happens for the state phi, because U is our presumed copier. And then we just take a scalar product sidewise of these 2 equations.
Which 2 equations?
This and that.
So these both, because your pointer is on the top. So yeah. No.
Sorry. All right. So this acts on this, and that acts on that.
I think your arrow is a little bit upper than the
yeah.
Sorry.
Okay, so now I see.
Is it clear now?
I guess it becomes a bit more clear now. Yeah, I don't want to ask too much.
No. Yes. I mean, I would like to explain. So I don't see how the pointer actually what pointer shows, but you see this equation where U acts on phi tensor S.
Yes,
right?
That's what I understood from what you said. Yes. So
and it is supposed it's a proof ad absurdum. So we are supposing that it is able to produce 2 copies of psi, right?
Okay.
And now we can do the same procedure for some other state phi. So U acts on phi tensor S and produces 2 copies of phi. And now we are trying to compute the scalar product between the left-hand sides of these two equations and right-hand sides of these equations.
Okay, so the inner product of the tensor product. Okay,
Yes, exactly. Excuse me?
So it's the inner product which you are forming in the tensor product space.
Yes.
Mm-hmm.
On the right-hand side, for sure, yes. Yes.
And then you use the unitarity again, and that drops out into this in the right.
Yeah.
Path.
Yeah.
Okay,
This is maybe you have heard of so-called Schrödinger picture and Heisenberg picture.
Yes. Yes.
Yes. So you see, in a way, the left-hand sides are being operated in the Heisenberg picture. I first work on operators inside the bra and cat. And on the right-hand side, I carry out the unitary and I work on states directly.
I see.
Yeah?
Yes. Yes. Yeah. Yeah.
Mm.
Thank you. Thank you.
Mm.
I guess I
You're
got
welcome.
a bit of better idea.
Oh,
It was
I'm
just a
happy.
question of the linear algebra. So
Yeah.
whether it just this equality is a result of pure linear algebra. only.
Yes, yes, pure. Exactly, yes.
Okay, thank you.
Mm-hmm. You're welcome.
Okay, thank you. Okay, a question from here.
Okay, I would like to ask a following question. So, okay, we expect that we know, in fact, that quantum computers would be more efficient at solving some problems, which in principle can be solved classically.
We don't know that. We start to know that. We just have one example that suggests it may be so, the Shor's algorithm. But in fact, there are no proofs that more efficiently classical algorithm or some other quantum algorithm cannot be constructed. So this is, I just wanted to stress that.
So,
Yes,
okay.
Schrödinger's algorithm is just an instance. Shor's algorithm is just an instance, but there are no proofs that equally efficient or even more efficient classical algorithm cannot exist. So it's a really open question if quantum computer is really capable of delivering any new capabilities in terms of computational
Okay,
power.
so there is no proof, but there is a hope that this is so.
Exactly. Yes.
People
Yes.
believe it. Okay, and my question is the following: there are certain problems, in fact, in pure mathematics, which okay, they are not complex in the sense that you need more computational power, but in fact they are unsolvable, meaning that there is a proof that there is no algorithm, for example, the word problem for groups and so on.
Yes.
So what is the status of these problems regarding quantum computing? So is there any instance of a problem which can be solved?
No, because you referred probably to the thank you, undecidable problems. Undecidable problem is a problem for which an algorithm cannot be formulated, but a quantum computer also requires an algorithm. It's just a quantum algorithm, and that's it. But quantum algorithm is also a sequence of very well-defined procedures. It's just carried out in a different way. What's the difference between quantum and classical algorithm? The chief difference is that quantum algorithm is carried out. You can imagine that quantum computer acts like a parallel computation, thanks to quantum superposition. So it's like a parallel computation, as if you had many computers working simultaneously in parallel, each on a different instance of your problem. And this is being done simultaneously in time. And this is it. So if parallel computation cannot solve something, quantum computer also will not solve it.
Okay, okay, thank you.
But this is a very interesting question, and in general, tracing the undecidable problems in quantum mechanics is a very interesting problem. I find it interesting for myself, but not only. There are several interesting results that can be found in literature. So trying to marry the two fields is an open problem and very fascinating.
I heard recently of something which is called gap labeling conjecture, which turned out to be undecidable, and this is somehow related to the quantum
This
mechanics.
is a problem in gap labeling.
Gap labeling conjecture, yeah.
Okay, I have not heard about it, but there is another result that is very interesting, that certain groups of Hamiltonians that, excuse me, Hamiltonian is an operator, Hermitian operator, that describes the energy of the system and governs its whole dynamics. So it's kind of chief for defining the quantum system. So there are groups of Hamiltonians, excuse me, that are very simple, in fact, because they involve just next neighbor interactions for systems that are two-dimensional, barely two-dimensional, so lattices with next neighbor interactions, for which if we increase the size of the lattice, whether this Hamiltonian has a gap, spectral gap, so whether this lattice is a semiconductor or it's not, is an undecidable question.
Yes, so I think that you are referring exactly to this
it's the same.
conjecture which
Okay.
I meant.
Okay, okay.
Thank you.
Yeah. Thank you.
I also wanted to ask a question. So this, as I understand it, it's not that we know that, okay, in the next 15 years or so, quantum computers will just be present everywhere, right? We don't know it.
I think in general, no, we don't. No one knows that. So quantum computers, they are the most, there is a lot of PR in quantum computers, and they are very, very much present in media because they attract attention. But I think out of all the quantum technologies that we have in hand, this is the one which is posing us most open questions. So there are a lot of open questions in this field. So we don't know. And as I earlier have said, quantum computer is not just quantum hardware on which everyone is focusing, because all these giants like Google, IBM, and others are actually advancing hardware, quantum hardware, due to the fact that the technology, nanotechnology, is advancing very much. But the quantum computer, its power stems from quantum algorithms, and we don't have these algorithms. Please, if you go back to these scientific papers that are demonstrating the quantum computer achievements, the quantum supremacy, that in 1 second something can be done in 10,000 years on classical machines, please have a look what they actually do. What is this thing that they do? They don't do anything useful. They don't carry out any reasonable, useful algorithm that we would like to have. The only one that we have in hand is the Shor's algorithm, that indeed exponentially accelerates the computation with respect to the best, most efficient classical algorithm doing the same job. But the other algorithm that we have, the Grover's algorithm, just gives us the quadratic speed up. So it's not so great. Obviously, there are some variants of this Grover's algorithm and related algorithms. So it seems there is a lot of them, but in fact, this is just one group. Beyond that, we don't have really anything that we can run on this computer. So this is a very big open challenge to find to formulate quantum algorithms. I find it fascinating as well. I don't think that I can probably formulate one such, but anyway, I would like to try.
Okay, thank you.
Thank you. Are there any other questions?
Okay, so as I understood, you said that okay, there is no proof that the Shor's algorithm is in fact more efficient than the possible classical algorithm. So what would be a possible strategy for proving a result like this? Since usually when you show that something is, for example, undecidable, the usual strategy is to somehow formulate this problem, reformulate this problem to something which is equivalent and is known that it is undecidable. But in this case, is there any, at least one instant when you can use something which is already known or not?
It's a good question, but you know, it's a very difficult task because you would have to basically rule out of infinite number of possibilities. I don't think that it is possible. In fact, a better approach, more efficient, I think, is to try, this is what's being done, is to try to actually find a generic, more universal proof that certain class of machines for a certain classes of problems is more efficient than classical computer. I don't know how to do that. I don't know if anyone has tried, in fact. But just at the end, I would like to tell you that, of course, people are trying, doing their best to try to invent new algorithms, because indeed there is high demand for them. And every now and then something is announced that, I don't know, by a renowned professor, you know, Harvard or something. And then 2 weeks later, a teenager on his, you know, laptop in his room just cracks it with a better classical algorithm, you know. So it's a very one has to be, we are walking on a thin ice, so to say, you know, when we are saying, okay, this quantum algorithm is better than anything the classical computer can do. And this actually, all these kind of claims that we would like to make motivated people very much to studying actually the boundaries of classical computer. Do we really know what are the limits of classical computer at all? We know what we usually do with the machines that we have that are universal on our desks, but obviously there can be non-universal machines that are more powerful for certain classes of problems and less powerful for some other, at the expense of some other. And so it's a really, really open, big question, how to show that a quantum machine will be provably better than any other possible classical machine.
I see. Thank you very much.
Thank you.
Are there any other questions, either here on site or on Zoom? Well, if not, that let us thank again the speaker.
Thank you very much.
Thank you.
Thank you for your
coming
interest.
here.
Thank you. Have a nice day then.
Yes, thank you. Let me stop the recording now.